Hello everyone, welcome back to the second part of this lecture. In this part, we are going to talk about lubrication approximation and thin film equation. What we are going to study in this part of the lecture is very relevant to the ongoing research projects in our field. And in that spirit, I'm first going to show you a video. This is one of my favorite videos, and some of you might have seen this video because we offered this project as a part of the bachelor and master assignment at Physics of Fluids group. So this video has been shot at the International Space Station. Scott Kelly here is an astronaut, and what he is doing here is he's playing ping pong with a liquid droplet. In fact, he's playing ping pong with a water droplet. And you can see that this water drop bounces off from this super hydrophobic rackets, and then he is able to just play along with it. So what we study in such a system is actually the flow field inside the droplet and outside in the air, along with studying the viscous dissipation in the system. So in this figure, so this one now I'm going to show you a numerical simulation, a direct numerical simulation of what you saw in the earlier video. And this is a water droplet with a green outline, and all around you see a velocity field. So the velocity vectors have been marked. On the right hand side, you see the velocity magnitude. So the droplet has the maximum velocity. And on the left hand side, you see the log 10 of the viscous dissipation term. And then wherever you have dark colors on the left, there you have high viscous dissipations. Where you have lighter colors, there you have low viscous dissipation. And let me play this video. So you see that the droplet comes down, uh, falls on the substrate, spreads, and then retracts back and then takes off. This is exactly what you saw in the video as well. Now I will slow down the video and I want you to focus on the thin gap between the drop and the substrate. And as you can see, as the droplet approaches the substrate, the air between the drop and the substrate needs to go out from the gap. And you can see there are very high velocities of air being escaped out of this thin gap. And what we are going to study today will be very relevant for understanding the flow that happens in these thin gaps. Let me start by giving you some more examples of such flows. Imagine that you have two surfaces which are separated by a distance h. This surface on the top need not be stationary and it might move up and down. So as it moves up or down, if there is a flow in the gap, this flow in the gap can be described by something that we call lubrication equations. One of the real life examples of such a flow could be in a ball bearing. Furthermore, we can have a case where a free surface is approaching a solid wall. This is similar to the case of drop impact on surfaces that we saw in the video. Now, one way in which these kind of cases are different than the previous one is that over here on both the surfaces, we have no slip boundary condition. Whereas when you have a case where a free surface is approaching a substrate, then we have something called a free slip boundary condition for the free surface. And that's how these two cases would be different. But nonetheless, the flow in this thin gap can always be described by using a set of approximations that we will come to know as lubrication approximation. Usually, there are two length scales associated with flows like these. First would be a vertical length scale, which I'm going to call H in this problem. And then there could be another length scale, which is L, as shown in the schematic. And we can define a parameter called epsilon, which is nothing but the ratio between H and L. And one of the important characteristics of the flows that we are going to study will be that this epsilon will be way smaller than 1. In order to describe the flow, let us write down the relevant equations that we have. The first is, of course, the continuity equation. Again, I'm going to assume that the liquid is incompressible. One thing that you can immediately see in such flows is that if the continuity equation has to hold, then U over L, U naught over L, so let's call the horizontal velocity scale as U naught. So U naught over L will have the same order of magnitude as v naught over h, where v naught is the vertical velocity scale. And the moment I write that, we can write v naught over u naught would be of the same order as h over L. And h over L we know is the parameter epsilon that we have defined. And as we have seen that this parameter epsilon is much smaller than 1, which implies that v naught will be much smaller than u naught. Next, we can write down the momentum equations, which is, so this is the x momentum equation, and this is the y momentum equation. Now, let us try and non-dimensionalize these equations. And for that, we will use the velocity and length scales as we have seen in the previous schematic. We can replace u by u tilde times u naught, x by x tilde times L, and we can replace t by t tilde times u naught by L. Again, similar to the previous Stokes law problem that we had, of course, we are going to assume that the time scale is L over U naught. Note that this time scale is similar to having T over V naught over H. And that's because U naught over L is of the same order of magnitude as V naught over H. Then in the Y direction, what we have is we can replace V by V tilde into V naught, Y by Y tilde into H. So once we plug in all the mappings as we discussed before, these are the final equations that we get. Note that I have used another scale over here, which is the pressure scale P naught, and so the pressure would be replaced with P naught times P tilde, as you can see over here. Now, with these equations in mind, let us try and use the lubrication approximation that we introduced in this lecture, which is to say that epsilon is much smaller than 1. By the way, this epsilon much smaller than 1 is also known as the long wave approximation. So the long wave approximation, the lubrication approximation, or the thin film approximation, all three terms mean the same thing, that we are going to introduce epsilon, which is the ratio of the length scales, and we are going to assume that this epsilon is way smaller than 1. Now, once we do that, we see that there is an epsilon square term over here. So this term will vanish because if epsilon is very small, then epsilon square will be even smaller. Similarly, the epsilon to the power 4 term will vanish, and so will the epsilon square term again. Note that I'm not cancelling out the pressure terms, because if I cancel out the pressure terms, then the flow becomes boring, as we have seen in the Stokes lecture. Moreover, we can always define a pressure scale P naught such that the pressure term is relevant. So we are going to leave the pressure term as it is. Furthermore, we are going to put in another assumption, which is that epsilon square REL is much smaller than 1. And once we do that, the left hand side of the x momentum equation vanishes, and the right hand side of the and the left hand side of the y momentum equation vanishes as well. So after we cancel out all the small terms, the relevant terms that are remaining are, for the x momentum equation, we have del p by del x is equal to mu times del square u by del y square. For the y momentum equation, we have del p by del y is equal to 0. And of course, the continuity equation remains the same. So know that all these approximations imply that epsilon is much smaller than 1, which is to say that h over L is much smaller than 1, which also means that any changes in the x direction is much smaller than any changes in the y direction. So this image on your screen right now gives you a clear picture of what we mean when we talk about lubrication equations, thin film equations, or long wave approximations. Now let us talk about the continuity equation. One way of reaching a relevant form of continuity equation would be to integrate this equation in this thin film that we have. However, I'm not going to use the integration approach. What I will use is the control volume approach. But you can always try and integrate this equation in this thin region and get the same relevant equation that you will see later on in the lecture. So here I'm going to use a control volume approach to find a relevant continuity equation. Let us assume that the volume flux coming in from the left of this control volume is Qx, and the volume flux exiting from the right is Qx plus dx. And this height h of this thin film is h, which is also a function of x. So from continuity equation, we can write that d by dt of h dx, so that's the time derivative of this volume that we have in the control volume, is equal to qx minus q of x plus dx. And of course, q of x plus dx we can write using the Taylor series expansion, which is qx plus dq by dx times dx. And if we plug this in, what we get is dh by dt dx is nothing but minus dq by dx into dx. And so very easily we get this continuity equation relevant for the thin film flows, which reads that dh by dt plus dq by dx is equal to 0. So here, once again, I have summarized the lubrication equations for you. And now we can integrate the momentum equation, and we can do so because for pressure, we don't have any y dependence. So once we integrate it, what we get is u is equal to half of dp by dx y square by mu plus c1y plus c2. And now if we plug in the first boundary condition, which is that u is equal to 0 at y equal to 0, we get that C2 is equal to 0. So the equation will now read u is equal to half of dp by dx y square by mu plus c1y. Now, moving forward from here, we can have one of these two cases. We can have a case where at y equal to h, there is a no slip boundary condition. Or we can have another situation where at y equal to h, we have a free slip boundary condition. Again, the case on the left could be a case where a solid sphere is impacting a wall, for example. And one of the examples of the case on the right could be a droplet impacting on a substrate, which is what we saw during the start of this lecture. Now, depending on one of these cases, we will have different boundary conditions. Now, depending on which case we are in, we will have a different equation. For this, we will have that u at y equal to h is 0, which means that C1 is equal to half of 1 by mu dp by dx h with a minus sign, of course. And then we get u equals to 1 by 2 mu dp by dx y square minus yh. Whereas for the other case, what we will have is that du by dy at y equal to h is equal to 0, which will give me that C1 is equal to minus 1 by mu dp by dx times h, and this will give me the equation that u is equal to 1 by 2 mu dp by dx y square minus 2yh. So depending on which case we are dealing with, either it is a no slip boundary condition at the top, or it is a free slip boundary condition at the interface, we can have one of these two cases. Now, if you remember in the continuity equation, we had dq over dx. So we need to find q, which is nothing but the volume flux at any given x. So let's calculate the volume flux at any x. And that will be nothing but integration of u dy from 0 to h. On solving the integral for the first case, we will get q is equal to minus 1 by 12 mu dp over dx times h cube. And for the second case, we will get q is equal to minus 1 by 3 mu dp over dx into h cube. And if we plug these equations back into the continuity equation, we get, so the first step while solving such problems would be to identify what kind of boundary conditions we have at the top of the domain, and then try and figure out which are the relevant equations that we need to use. In such flow problems, we are usually interested in two key variables. One is the height h as a function of x and time, and second is the pressure as a function of x. So usually you will either be given the evolution of h as a function of space and time, and then you would be supposed to calculate the pressure drop inside the thin gap, or you would be given the value of pressure or the evolution of pressure, and then you will supposed to find the evolution of the thin film height h. And we are now going to look into two examples of doing exactly that. So in this example, we have a flat plate which is falling down with a velocity v naught, and somehow I'm going to keep this velocity v naught constant, and this plate is falling on the ground, and at some point it is at a distance h away from the ground. I'm going to assume that the length of the plate is 2L, and that this h over L is much smaller than 1. So once I do that, then I am satisfying the lubrication approximation that we had earlier. So clearly, in this problem, we know that there is going to be a no slip boundary condition both on the top plate as well as on the bottom plate. Furthermore, we already know that dh by dt is nothing but minus v naught. And of course, since these are both flat plates, the height h will be independent of x. So h will not depend on x. And then we already know that dh by dt is going to be minus v naught. So these things we already know. And from the lubrication equation relevant for this kind of flows, we have that dt by dh minus 1 by 12 mu d by dx of dp by dx times h cube is 0. And we know that dh by dt is minus v naught. What I get is v naught plus 1 by 12 mu d by dx of dp by dx h naught minus v naught t cube equal to 0. So this is h. Now we can integrate this equation in x, uh, realizing that h is independent of x. The constants of integration c1 and c2 can be found by applying boundary conditions, and the first boundary condition would be that dp by dx is 0 at x equal to 0, and this is because of the symmetry of the problem. So this will give me that c1 is 0. Furthermore, pressure P at x equal to L will be equal to P naught. So at the edges, the pressure will be equal to the atmospheric pressure. Let's call it P naught. So if we apply this in and then rearrange, what we get is that P is equal to P naught plus, rewriting, we get. So in this problem, we knew the evolution of h as a function of time, and then we were able to calculate the pressure inside the thin gap. What we can also do is to calculate the force being applied on the top plate, and that will be nothing but this value. Among performing this integration, we will get that the force is equal to 8 mu v naught L cube by h cube. So this force F is the force that is being applied on the top plate as it falls down. And as you can see, as h tends to 0, this force becomes infinite. So there is a very high lift force being applied on the top plate as it comes closer to the bottom plate. And now this is a part of the lecture where usually I throw some A4 sheets paper around to show you this phenomenon in practice. However, unfortunately, I cannot do this right now, so I'm going to call in the big guns and we'll go back to the lecture by G.I. Taylor and let's see what he has to say about the topic.
A very simple experiment can demonstrate that the coefficient of friction, which is the ratio of the tangential to the normal force between two bodies in relative motion can be much reduced by hydrodynamic lubrication. Holding this sheet of paper horizontal, I give it a slight forward movement and drop it. It slides quite a distance. As it settles, the air is forced out of the narrow space between it and the table. The tangential stress so produced enables enough pressure to be built up beneath the notepaper to support it for a time. And during that time, the friction retarding sideways motion is very small. If a few holes are made in the sheet so that the air can escape without passing under its outer edge, it stops much more quickly.
So that was quite interesting. As you saw that when the paper comes very close to the top of the tabletop, it has a very high lift force because of the thin air cushion between the paper and the table, and that's why the paper can glide on the table. However, if you puncture some holes in the paper, then of course that air will escape out, and then the paper will immediately touch the table, and then we won't be able to appreciate these lubrication forces. So now we are going to look into the second type of problems that we often encounter with lubrication flows, and this is the case where we have a thin film which is on top of a wall. Now in this thin film we have provided some disturbances on the surface. So let's say that this film height h is nothing but h naught, which is the mean height of this thin film, plus delta times sine kx, where delta is the amplitude of the oscillations that you see on the thin film, and k is related to the wavelength lambda as lambda equals 2 pi by k. So of course we already know what lambda and k is, and we know what h naught is, and we would like to know how delta behaves in time. So the idea would be, can we find this delta as a function of time? And for that, let's write down the relevant equations. So we have dh by dou t is equal to 1 by 3 mu d by dx of h cube dp by dx. And of course, we have that d rho p by dou y is 0. For this problem, we first need to understand what is the value of this pressure. So of course we know that the partial derivative of pressure with respect to y is 0, which means that pressure in the y direction is same. But now we have an interface between the liquid and air, and this interface will be and this interface will have a surface tension coefficient sigma. So what this surface tension does is that it introduces a Laplace pressure at the interface, which means that the pressure at y is equal to h can be written as, this term over here is the curvature of thin film at y is equal to h. Now, of course, since we are in the long wave approximation limit, we are going to assume that dh by dx is much smaller than 1. And so we get the pressure at y is equal to h is nothing but minus sigma times del square h by del x square. Now, once we plug this in, we get, so therefore, the pressure gradient will be, well, let's go and put this inside the lubrication equation that we had earlier. So this is the final form of the equation which will be relevant for solving this problem of relaxation of thin films. Now we already know some of the derivatives that are involved in this equation. So let's try and find them out. So we know that h is equal to h naught plus delta sine kx, which means that dh by dou h by dou t would be, furthermore, dh by dx will be The double derivative of h with respect to x would be, and of course the final third derivative would be. One last assumption that I'm going to make is that h cube can be written as h naught cube. So I will assume that since these oscillations are tiny, that I can ignore them when I compare them with h naught. And so I can simply write h cube as equal to h naught cube. So what we get after we plug in this equation back into the lubrication equation is, so we have to differentiate it once more. And now what we are left with is an ordinary differential equation, which is also linear. So we can solve this equation. At the end, we get delta equals, and this is the classical example of relaxation of thin film, where the amplitude of oscillation, delta, decays with time. And the lubrication equations are very relevant for many of the ongoing research topics. For example, one of the research topics that we have in the group is the spreading of this sessile drop on a substrate. So imagine that you have a droplet, and you place a droplet on a substrate, and then that droplet spreads on top of the substrate. And there you can see that if the contact angle is small enough, then you can approximate the flow by using lubrication equations, because the gap, the height of the droplet would be much smaller than its lateral length. Furthermore, if you zoom in towards the corner of this droplet, then there you will see a contact line spreading on top of the substrate, which is very similar to the Taylor scraper problem that we saw. So this is nothing but a viscous corner flow, and with a contact angle theta. So as you can see that these lubrication equations and the long wave approximation that I just introduced you to is very relevant and important in the field of fluid mechanics.